Welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this is part 3 of Trigonometric Identities. In part 1, I introduced you to the basic identities, and I've just written them here. We talked about the reciprocal identities, which are these first 6 identities. Then I showed how tangent of theta was equal to sine of theta over cos of theta, and similarly cotangent, because it's the reciprocal of tangent, would be the reciprocal of this ratio, so it's cos theta over sine theta. I also showed you the Pythagorean identities and why they are true, and the idea with proving identities is you take these 11 basic identities as well as some different algebraic techniques to prove further identities. In the second video, I did show you some examples of proving some other trig identities. And in this video, I want to take a look at some more challenging identities that you might encounter. So let's get started. In my first example, I have tangent of x plus cotangent of x equals this. This isn't an equation, it's asking me to prove that this is equal to this. You can choose either the left-hand side or the right-hand side of the identity and manipulate it until it looks like the other side. I'm going to choose this, and the strategy I'm going to use initially is I'm going to write tangent x and cotangent x in terms of sine and cos. Tangent of x is equal to sine of x over cos of x, and cotangent is equal to cosine of x over sine of x. Instead of rewriting this, I'm just going to put RHS for right-hand side. A little bit of a shortcut that I use. Now, in order to do anything with this, I'm adding fractions. I need a common denominator. So my common denominator will be cosine x times sine x. So I need to change these two fractions to equivalent fractions with that as the denominator. The way that I'm going to do that is I'm going to multiply numerator and denominator of this fraction by sine of x. Similarly, I'll multiply numerator and denominator of this fraction by cos of x. And you're allowed to do that. You're allowed to multiply both numerator and denominator by the same factor without changing the value of the fraction. Then I'm going to have sine squared x over sine x cos x plus cos squared x over sine x cos x. Once I have a common denominator, I can combine my fractions. I combine my numerators over that denominator. So I'll have sine squared x plus cos squared x over sine x cos x. Unfortunately, I can't keep going down, so I'm just going to need to scoot over to the side here. If I take a look at my Pythagorean identities, sine squared x plus cos squared x is equal to 1. So you typically do one step at a time when you're doing identities. You're trying to show why this is equal to this, and if you try to put in too many steps at once, the person who's looking at the proof might get lost. So you want to make sure that it's clear the logical steps that you're taking. Now we take a look at what the right-hand side actually is. It's secant x times cosecant x. That will help you to determine what your next step is. So what I'm going to do is I'm just going to break these. I'm going to break this fraction up into the product of two fractions. If I were to multiply these two fractions, I would get this. And we know 1 over sine x is cosecant x. We know 1 over cosine x is secant x. We've got the same product, maybe change the order so it looks identical. And once it's identical, you're done the proof. Let's take a look at another example very similar to this one. In this next example, I want this, my left-hand side is exactly the same as in my last example. but my right-hand side is different. So I would start this proof the same way I did in the last example. I would go through this process. The problem is I wouldn't be done at this point. Like I mentioned, I'm looking to see what I want as my final expression. So I look at where what I've obtained, and I try to decide how do I get to there. So in this case, I'm wanting tangent. Again, think of tangent in terms of sine and cos. Cosecant, think of it in terms of sine. It is possible if you get to this point, and then you can take a look at this side and manipulate this side until it's equal to this. That's acceptable, as long as you're only manipulating one side at a time. You might find that easier now at this point to go, okay, let's see what I can do with this. I'm kind of stuck here. Let me play around with the right-hand side and see if I can make it look like that. Perfectly acceptable. I'm just going to continue with this, however. I want cosecant squared, which I know is 1 over sine squared, and I want tangent, which I know is sine over cos. That means if I were to multiply the numerator and the denominator by sine of x, I'm not changing the value, so I'm going to do that. Sine of x over sine of x times sine of x, which will be sine squared of x, times cos of x. Now I'm going to write this as a product of two fractions. So I'm going to write it as 1 over sine squared x times sine of x divided by cos of x. If I were to multiply these two fractions, I would end up with that. Now I can express 1 over sine squared x as cosecant squared x. Sine of x divided by cos of x is tangent of x. And if we want to have it exactly that in that form, I can just change the order. It's identical, so I'm done my proof. Let's take a look at some other possible types and the strategies for solving those. By the way, I'm grabbing these examples from this textbook, Basic Technical Mathematics with Calculus by Alan Washington. In my next example, avoid the temptation to cross multiply. This is not, you're not solving an equation. You're trying to prove something. So I'm going to again work with the left-hand side. It really doesn't matter in this case. It's the same amount of work either way. And I'm going to use my Pythagorean theorem, cos squared x plus sine squared x equal to 1. And I'm going to isolate sine squared x by subtracting cos squared x from both sides. So I'm going to use the identity to replace this expression with this. And you might look at this and say, well, Laurel, you don't have this. I don't, but I can make it. Remember that if you have a plus b, and if you multiply it by a minus b, it becomes a squared minus b squared. That's the difference of squares. I'm going to use that concept to get a difference of squares in the numerator that's actually going to be equal to this. So what I'm going to do is multiply by 1 minus cos x. So I have 1 plus cos x. I'm going to multiply by 1 minus cos x. Whatever you multiply the numerator by, you must also multiply the denominator by the same thing. And I'm just going to put right-hand side here. Now I can multiply those and I will get 1 minus cos squared x. Difference of squares. Resist the temptation here of canceling terms. You can't cancel terms, you can only cancel factors. And we don't have any common factors yet. I know that 1 minus cos squared x is equal to sine squared x. Now I have a common factor of sine x in the numerator and in the denominator, so I'm going to cancel. I'm going to divide sine x into the denominator and divide it into the numerator, so I'll be left with just 1 sine x. Take a look. I've done my proof because my expression has been manipulated using my identities and some algebraic techniques to get that. This identity looks brutal, and a lot of people are intimidated by that, but I'm going to walk you through it. Don't be too concerned yet. I'll show you another strategy that involves factoring. But the problem is that we have sine squared theta and we have cos theta. That's going to be an issue. So what I want to do in this case is I want to just have one of those trig functions. And so I'm going to replace the sine squared using my Pythagorean identity here. I know that sine squared x will equal 1 minus cos squared x. I'm going to replace sine squared theta with 1 minus cos squared theta. And just stick with this. I'm going to show you why I'm doing that. So sine squared theta will be 1 minus cos squared theta. I'm going to do the same thing in the denominator. I'm going to replace sine squared theta with 1 minus cos squared theta. And I'm going to combine like terms. So I've got negative cos squared theta plus 2 cos theta, and I have 1 minus 1, so it's gone. In the denominator, I have negative cos squared theta plus 3 cos theta. 1 minus 3 is minus 2. I have an expression in the numerator that I can factor, and I have one in the denominator that I can factor as well. But typically when you do factor, it's easier to factor if you make your leading term, your highest degree term, positive. So I'm just going to multiply the numerator and the denominator by negative 1. So I will get cos squared theta minus 2 cos theta. So I'm multiplying everything by negative 1. I'm going to do the same thing in the denominator. And I'm going to get positive cos squared theta minus 3 cos theta plus 2. If I were to factor in the numerator, I would factor out a cos theta. And I'm left with cos theta minus 2. In the denominator, my factors will be cos of theta minus 1 times cos of theta minus 2. Now I have a common factor of cos theta minus 2 I can cancel. So I'm left with cos theta over cos theta minus 1. I look and I go, that's not quite what I want, but I'm almost there. I want a 1 in my numerator, and I want a 1 minus secant theta in my denominator. I can get all of that if I divide the numerator by cos theta and the denominator by cos theta. So in other words, I'm going to multiply by 1 over cos theta in the numerator and 1 over cos theta in the denominator. So 1 over cos theta times cos theta will be a 1. 1 over cos theta times cos theta will be a 1 minus, remember you have to distribute. When you're multiplying an expression, that you have to multiply every term. So 1 over cos theta times 1 will be 1 over cos theta. We're almost there. 1 over cos theta is indeed secant theta. So I don't have room. So I'm just going to erase this and replace that with secant theta. So these proofs are not easy. I admit that, but they do get easier when you do more of them. My next video is going to be on double angle identities for the sine and cosine function. So when you're ready, I'll see you on the next video.